Hello everyone, my name is Timmy. I'm an incoming computer science PhD student at the University of Chicago. Today, I'm really excited to share our work titled ThrowIO, Actuated TUIs that facilitate throwing and catching with overhang mobile wheeled robots. Designing spatial and tangible user experience has been a great interest in the HCI community. However, very few papers focus on the affording design opportunities for throwing and catching, which is also an important user interaction in spatial experience. Inspired by my personal interest in juggling, we want to design an actuated tangible user interface that can facilitate throwing and catching real objects. We thus present ThrowIO. By simply placing two robots on an overhang surface, users will be able to vertically throw and catch a magnetic object in different scenarios. Once the object is thrown and stuck on the ceiling, the robots will be able to push and drop them at different locations, allowing users to spatially interacting with them. ThrowIO is building contribution upon prior research in robotic juggling, ceiling robots, swarm user interfaces, and VR throwing and catching. Comparing to prior work in robotic juggling, ThrowIO has the advantages of having easier robotic control and lower deployment cost. Comparing to the previous research in VR throwing and catching, ThrowIO offers real-world throwing and catching responses and allows spatial interaction without head-mounted display. ThrowIO's contribution includes a novel approach in facilitating vertical throwing and catching with overhang robots, a design space overviewing the system components and enable interaction, a proof of concept implementation using ThrowIO robots and computer vision tracking, and lastly, applications in a wide range of utilities in tangible and spatial interaction. The design space of ThrowIO includes a basic architecture of an overhang surface, wheel robots, and thrown objects. The core interaction involves users throwing and catching objects with the robots. The height of the overhang surface can also be adjusted for different needs, such as a height on the ceiling, at the chest height, or under table. The thrown objects can also have various sizes or be other everyday objects as well. For example, we can throw an orange ball with the size of a ping pong ball, a red ball with the size of a tennis ball, and a heart-shaped object. The spatial user experience in ThrowIO can also be enhanced by graphical augmentation, such as a vertical monitor display for a basketball game or an overhang projection for an immersive haptic experience. Just like this. To illustrate the idea of ThrowIO, we built a proof of concept implementation that involves a ferromagnetic surface, two overhang robots, a magnetic thrown object, and Connect Depth camera. We use a Connect Depth camera to track an orange thrown object that has a diameter of 4 cm and circular magnets covered. We have chosen this orange ball in our implementation because it is easier to be stuck, pushed, and dropped compared to other prototypes we tested. The sticking performance of the orange ball is evaluated using a slingshot mechanism, and we found an optimal range to throw this ball with different speed and angles. You can refer to the paper for more details. The ferromagnetic surface is designed by placing a metal plate under a height adjustable table, such that the height can be changed for different purposes. The overhang robots is designed by placing a ThrowIO robot into a customized 3D printed mechanical shell. This shell has a prong side and a wedge side that are used to perform push and drop operations. This is a push operation, and the drop operation require two robots to drop the ball together. We developed the robot movement control algorithm for pushing and dropping, responding to computer vision input. So with the idea of throwing and catching different objects at different height, and also with different graphical augmentation, ThrowIO is able to demonstrate many different applications. In this immersive haptic experience application, a user is invited to an orange picking story. They were asked to throw a ball to wake their bird companion up, which would then fly to drop oranges for the user. When a virtual orange is dropped, it is accompanied by the dropping of a physical ball. This experience allows users to tangibly interact with items in the projected digital screen. In the ceiling storage application, a user is throwing a ball that has a key attached to it. Once the items are stuck to the ceiling, the robots will push and store the items in the storage area. A user can also retrieve the item by placing their hand under the ceiling, and the robots will drop the objects to their palm. In the UFO game, a user throws a physical ball that will translate into a vertical display as a cannonball to hit the UFO. And on the left corner, you can see how the robots actually drop the ball behind the scenes. Once the user hit the UFO, a new cannonball will be fed to them, followed by the dropping of a physical ball as well. ThrowIO can also support another game called the basketball game, where a user can try to shoot balls into a basket. This game uniquely shows the existence of multiple balls in a basket, while in reality, the experience is only handled by one physical ball. ThrowIO is also able to support remote communication where two users can throw a heart-shaped object with each other, under-table communication where users can pass a pen without causing distraction, and lastly, kinesthetic learning for users to learn how to juggle a ball. We conducted a user study with a goal to understand the capability and limitations of our current system, and also observe how participants interact and perceive our system. We asked our participants to join the immersive haptic experience, UFO game, and ceiling storage. We received many positive comments and got responses for their fair application and interaction setup. We also got suggestions such as improving the sticking performance of the thrown object. The exploration with ThrowIO and the user study reveals a wide range of future research opportunities. For example, the hardware can definitely be improved, such as designing stickier thrown objects. The surfaces and the number of robots and thrown objects can also be scaled up. In our lab, we have built a larger overhanging surface to test out this prototype. Since ThrowIO currently uses color-based object detection, more robust 3D object tracking tools such as OpticTrack can be used in the future to track objects. And lastly, we also aim to have our objects be dropped with different angles and speed, just like a ping pong ball machine. In conclusion, ThrowIO introduces a novel approach to facilitate throwing and catching with overhanging robots. Its design space allows a breadth of applications, and we really hope that our work can introduce a new direction on how users can spatially interact with physical objects using everyday surfaces. And before wrapping up, I would like to mention that there is actually another paper really close to the approach of ThrowIO presented in this year's SIGCHI from our lab, X Lab, at UChicago. And this work is called Aerobrick UI. It introduces another very exciting research in enriching everyday spatial and tangible interaction with on-ceiling swarm robots embedded with the bricking mechanism. So both of these papers were pushing to this really exciting approach in designing our everyday spatial interaction with on-ceiling mobile robots, which we hope the SIGCHI community is also really excited for. With that, I hope you get a chance to check out both of the papers and come to our joint interactivity demo. Thank you really much.